We're solving problem 1 from the 2025 AMY 2. 6 points A, B, C, D, and E, and F lie in a straight line in that order. Suppose that G is a point not on the line and that AC is 26, BD is 22, CE is 31, DF is 33, AF is 73, CG is 40, and DG is 30. Find the area of triangle BGE. So for this problem, we have all these points on a line, and we have all these measurements. We can let the lengths AB, BC, CD, DE, and EF be equivalent to variables A, B, C, D, and E respectively. So what we can do is then substitute these variables into these measurements we have here. So for instance, for the first one, AC is 26. We have A plus B is 26. And then we just keep on doing this process. So B plus C is 22. C plus D is 31. And then we have D plus E is 33. Then for this, since it's the whole length, it's just the sum of all these variables A to E. So A plus B plus C plus D plus E is 73. Now we see that for all these 4 above sums, there are sums of 2. So there's 2 terms being added for each one of these up here. And the total sum is a sum of 5 variables. Therefore, if we can substitute 2 of these equations into here, we can isolate a variable. So we can do that, and we want to isolate point C in this case. So we have A plus B and D plus E. D plus E is 33. A plus B is 26. 26 plus 33 is 59. And then we do 73 minus 59 to get that C equals 14. Then, because we have C equals 14, we want to find the base of this triangle, which is B plus C plus D, which is the entire length of the triangle, 73, minus A and E. So therefore, we use C equals 14 to find that, A plus E is equal to 34. Therefore, B plus C plus D must equal 73 minus 34, which is 39. Then, with these measurements, we can use Heron's formula to find the area of a similar triangle to the triangle we're trying to find, which is triangle CGD, which is square root 42 times 28 times 12 times 2, which is 168. As a result, because our desired triangle BGE is 39 over 14 times larger, we do 168 times 39 over 14, which gives us our answer of 468, and that is our answer for this problem. We're solving problem 2 from the 2025 AMY 2. Find the sum of all positive integers n such that n plus 2 divides the product 3 times n plus 3 times n squared plus 9. So, in order for this to happen, and we want to find the sum with this basically fancy z over here, we need this to be true. So first step we can do is pretty interesting one nonetheless, because it requires some amount of insight, because this is not something you typically do. This becomes equals 3 n plus. We know that we have an n plus 2 here, right? But we have n plus 3 n squared plus 9. However, we can cleverly see that 3 is equal to 2 plus 1, so that we do n plus 2 plus 1, n squared plus 9 over n plus 2. Okay, now this becomes 3 times n plus 2, n squared plus 9, plus 3 n squared plus 9 over n plus 2. Now we can just cancel out the n plus 2 on this side. So we get 3 n squared plus 9 plus 3 n squared plus 9 over n plus 2. Having trouble drawing the symbol there. But now we can even like further complicate this. So what we can do is basically all of this, we put it back under the n plus 2 to get 3 n squared minus 4 plus 13 over n plus 2, and this property remains the same. Then this right here becomes 3n plus 2 and minus 2 using difference of squares. And then we still have that 13 in the parentheses left over. So we just sum a 13 times 3, or 39, over n plus 2. Once again, the n plus 2 cancels, so we have 3 and minus 2 plus 39 over n plus 2. So we know that this n plus 2 has to be a positive integer. And we basically can just start listing out factors of 39 because we want the sum of the working factors. So 39 has 1, 3, 13, and 39 as factors. This results in n having, you have to subtract 2 from each of these. So we have negative 1, 1, 11, and 37. We know that we can't have negatives because it has to be a positive integer. So we have 11, 1, 11, and 37. So we want to find the sum, which is going to be 49. I don't know why I drew a box around that, but sum is going to be 49, and that is our answer for this problem. We're solving problems 3 from the 2025 AMC2. AME 2. 4 unit squares form a 2x2 grid. Each of the 12 unit line segments forming the sides of the squares is colored either red or blue in such a way that each unit square has 2 red sides and 2 blue sides. One example is shown below. Red is solid, blue is dashed. Find the number of such colorings. So we have a few cases here. Let's consider. So what we can do is we can count how many of the center ones are filled in first. So let's just look at the first case. If we have something like this, where all the center edges are filled in, this yields one way. For the second case, we wouldn't have 4 filled in, we'd have 3. So for every next case, you're subtracting the amount of edges in the center used. So if you have a configuration something like this, this would give you, well, you have 4 right now. 2 times 2 is 4 because of that, and then you have to multiply by 4 again to get the total number of configurations for this one, which is 16. For the third case, we're going to have 2 subcases actually. So the first type of case you can have with 2 lines is like this, and this would give you 2 times 2 is 4. 4 times 4 is 16 again. However, the next one, if you have a dot like this, and it's a straight line like that, This has number of ways of 2 to the power 4, which is 16. And we get 16 times 2 for the total number of ways this has, which is 32. Different colorings for that one. 32. For case 4, it's just going to be 1. This, we automatically can just see this has 16 different ways. And then case 5, which nothing in the center is filled in, this is 1. So we want to sum up all of our numbers here. We have 1 plus 16 plus 16 plus 32 plus 16 plus 1. So we get 64 plus 18, which is 82, and that should be your answer for this problem. We're solving problem 4 from the 2025 Amy 2. This product is equal to m over n, where m and n are relatively prime positive integers. Find m plus n. So basically, what we have here is this pretty big product with logarithms. The first thing we can do is we can rewrite this entire thing to be equal to 15 over 12 times 24 over 21 times, they give us the third term, but I just didn't have space to write it up here. It is log base 6 of 5 to the power of 35 over log base 7 of 5 to the power of 32. So it's 35 over 32, and we have 3968 over 3965 as our second to last product. Our last being log base 4 of 5 over log base 64 of 5. This product becomes, well, this simplifies to log base 4 of 64 times 4 plus 1, 4 minus 1, 5 plus 1, 5 minus 1. And this pattern keeps occurring until the last term, 63 plus 1, 63 minus 1. And it's divided by 4 plus 2 times 4 minus 2 times 5 plus 2, 5 minus 2, all the way until 63 plus 2, 63 minus 2. Log base 4 of 64 is 3, and then for this product we have 5 times 3 times 6 times 4 times all the way to 64 and 62, while the denominator has 6 times 2 times 7 times 3, all the way to 65 times 61. There's a recognizable pattern you can do to cross this out. So most of these terms cancel, leaving only a few behind, and this thing can eventually simplify all the way into 93 over 13, simplest form. So we have a fraction, which is this product simplified. So we just sum 93 and 13 to get our answer of 106, and that is our answer for this problem. We're solving problem 5 from the 2025 Amy 2. Suppose triangle ABC has angles BAC is 84 degrees, ABC is 60 degrees, and ACB is 36 degrees. Let D, E, and F be the midpoints of sides BC, AC, and AB respectively. The circumcircle of triangle DEF intersects at BD, AE, and AF at points shown. Find DE plus 2HJ plus 3FG, where the arcs are measured in degrees. So, we want to find DE plus 2HJ plus 3FG. Now we have all these degree measures up here. First thing we notice is that there are a lot of similar triangles in this problem because we know that some of these points intersect at the lines, splitting them in half. So we have triangle AFE similar to triangle FBD, which is similar to triangle EDC, which is similar to the big triangle, triangle ABC. Now, what we can do is, well, since these are all similar triangles, they should have identical sides or identical angle measures. So we know that we have some of the angle measures. ACB, I'll just write 36 there. From this measure alone, we can deduce one of the things we need to find in this problem, or actually two angles, which is arc DE. We can derive arc DE from this angle because arc DE is equal to 2 times angle EFD, which is equal to this angle because of similar triangles. So this is 2 times 36 degrees, or 72 degrees. We also have an arc length FG, and an HJ. So what we can do is we can keep on like angle chasing, I guess. Here we can do the basically same thing with FG. This is definitely not drawn to scale, but it's all right, I guess. So we can start solving. So if you have FG, arc FG will have an angle similar to this one due to the similar triangles, because there's another arc here that has an angle, starting angle 36 degrees, and FG for FG, so that's 2 times 36 is equal to 72 degrees again. Then we have a final angle, HJ, and we leave it to the last because it's the hardest to find. We know that angle BAC is equal to 1/2 of angle FDE minus arc HJ, or no, just arcs. We're not doing angles. We know that angle BAC is 84, and FDE, arc FDE, is, it's not good, like that, is equal to 360 minus arc FE, which gets us to 192 degrees for arc FDE. And then we can plug these values in. So BAC is 84. 84 is equal to 1/2 of 192 minus HJ. And we solve for HJ. Arc HJ is equal to 24 degrees, because this is 168, 168. I should probably just like double check. 2 times 84 is 168, and this is equal to 192 minus HJ. Arc HJ is equal to 192 minus 168 for 24 degrees. So, yep, it is 24 degrees. And now we have all our lengths, 72, 72, and 24. So we want the sum 72 plus 2 times 24 plus 3 times 72, which is 336 degrees, our answer for this problem. We're solving problem 6 from the 2025 AMY 2. Circle omega 1 with radius 6 centered at a point A is internally tangent at point B to circle omega 2 with radius 15. Points C and D lie on omega 2 such that BC is the diameter of omega 2 and BC is perpendicular to AD. The rectangle EFGH is inscribed in omega 1 such that EF is perpendicular to BC, C is closer to GH than EF, and D is closer to FG than EH as shown. Triangles DGF and CHG have equal areas. The area of rectangle EFGH is m over n, where m and n are relatively prime positive integers. Find m plus n. So, first thing we can do, we let the intersection of BC and omega 1, the smaller circle, be P. The intersection between BC and GH be Q. So that point, tiny one right there. R is the intersection of AD and FG, and we let the center of omega 2, the second bigger circle, be O. First thing we can do is set variables for the side lengths of the rectangle. The area of a rectangle is based on height, length times width. So we just set EF, which is equal to GH, to be A, and let's set FG to equals EH, because it's a rectangle, to be B. Then we have that point, that length CP is equal to 18, therefore PQ is equal to 6 minus B over 2. So we have these lengths now. We can now deduce from triangle OAD, the center OAD, that length AD is equal to, we have AD is equal to 12. We have this length now, and we can use it to solve for dr. dr is equal to 12 minus b over 2. So we have all the information necessary to make some sort of statement or claim. So we have a times 24 minus b over 2 over 2 is equal to b. 12 minus a over 2 over 2. This brings us to b is equal to 2a. We can use the Pythagorean theorem, and because we know the length of AD, we can say that a squared plus b squared is equal to 144. So we can plug that in to find a. We can substitute this in here to solve for a and b, and we eventually get that the area of the rectangle EFGH is 288 over 5, making our answer 288 plus 5, or 293. And we are done. We're solving problem 7 from the 2025 AMY 2. Let A be the set of positive integer divisors of 2025. Let B be a randomly selected subset of A. The probability that B is a non-empty set with the property that the LCM of its elements is 2025 is m over n, where m and n are relatively prime positive integers. We want to find m plus n. So what we want to do for this problem is, well, when we prime factorize 2025, it gives us 3 to the power 4 times 5 squared. So we want to so the problem asks us to find the sum of n plus n, where m over n is the probability that B is a non-empty set with the property that the LCM of its elements is 2025. So we can just break 2025 into prime factorization. We know that it's 3 to the power 4 times 5 squared, and it's asking for the probability. So we know we have to have a base of 3 and a base of 5. Now the powers do vary, which is where the probability comes in. So let's say the power for 3 is A and power for 5 is B. We then know that A has to be between 0 and 4, and B has to be between 0 and 2. This way, we have basically like this question in a more like simpler way we can solve. We see here that number of divisors of 2025 is 4 plus 1 times 2 plus 1, which is 5 times 3, or 15. Therefore, the cardinality of the set is 2 to the power of 15. Now we can consider some cases. This is pretty simple because we can just consider the cases of B where there's only 3 of them, for B being integers. If you have 3 to the power of 4 times 5 squared, the LCM is automatically 2025, and this yields 2 to the power of 14 cases. Now, if you have 3 to the power of 4 times 5, you can have one of these, but you can choose 9 other numbers, meaning that this will yield 2 to the power of 9 times 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4 ways, which is 2 to the power of 9 times 15. Likewise, we can do the same. If we have 3 to the power of 4, we apply the same logic here, and this yields us 2 to the power of 8 times 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4, which is 2 to the power of 8 times 15. Therefore, our answer is just simply going to be all these summed up. So 2 to the power of 9, because we can factor out something common. Basically, this is going to be 15 plus 30 plus 64, all over 2 to the power of 15, which is the total, again, cardinality. This gets us 109 over 128 when you just simplify, which you now have, right, as an expression of the probability that the problem wants. So our answer is going to be the sum of the numerator and the divisor, which is 109 plus 128, which is 237. And that is our answer for this problem. We're solving problem 8 from the 2025 Amy 2. For an unlimited supply of 1-cent coins, 10-cent coins, and 25-cent coins, Silas wants to find a collection of coins that has a total value of n cents, where n is a positive integer. He uses the so-called greedy algorithm, successively choosing the coin of greatest value that does not cause the value of this collection to exceed n. For example, to get to 42 cents, Silas will choose a 25-cent coin, then a 10-cent coin, then 7 1-cent coins. However, this collection of 9 coins uses more coins than necessary to get to a total of 42 cents. Indeed, choosing 4 10-cent coins and 2 1-cent coins achieves the same total value with only 6 coins. In general, the greedy algorithm succeeds for a given n if no other collection of 1-cent, 10-cent, and 25-cent coins gives a total value of n cents using strictly fewer coins than the collection given by the greedy algorithm. Find the number of values of n between 1 and 1,000 for which the greedy algorithm succeeds. So we have any number of 1-cent coins, 10-cent coins, and 25-cent coins. The example they give you is 42 cents, right? So this is basic. They're teaching us how the greedy algorithm works. So we have total sum of 42 cents. So you have to start from the biggest cent value, which is 25, and you want the greatest number of that biggest cent value first. So you can only have 125, and then you move to the next lower denomination, which is in 10 cents. You can, again, only have one 10 cent without going over 42. And then for here, you have to have 7 1-cent coins, which is not optimal because you can have 4 10s and 2 2s. Now, usually in these problems with these algorithms and equations, and you want to find how many values succeed between a very large range, say 1,000 numbers, 500 numbers, 100 numbers, there's usually a pattern. And again, what we're going to do is try to find a pattern and see if there is a noticeable pattern, and there should be usually in these problems. So what we can do, we first note that if the sum n is less than or equal to 25, the greedy algorithm automatically succeeds. But then we can start considering ranges, right? Like 25 to 30, they obviously succeed. But once you get to, you notice cracks starting to form here at n is 30 to 34. Because the optimal greedy algorithm way to get 30 is, well, you have to start with the largest. So 25, and then you can't have any 10s since it would go over 30, so you have to add 5 1s. This clearly is not optimal because the more optimal way, you could just have 3 10s. Again, you see at n from 40 to 44. Oh wait, shoot. There's the dash, 40 to 44. You see here that greedy algorithm says to get 40, you have a 25 plus a 10 plus 5 1s. Again, this is not optimal because you could just have 4 10s and that'll solve all your problems. So, but eventually, you see here that for every 25 values of n, we see that there are 10 values that do not work. So we therefore want to find the number of cycles of 25 such that we can compute how much don't work and then subtract that number from 1,000 to get our desired numbers that work. So in order to calculate that, we do 955 minus 30 over 25 plus 1 for the starting values we already have. This gets us to 38. 38 cycles of 25 where 10 values don't work. Since we want to use complementary counting, we need to find the number of numbers that don't work. So since there's 10 numbers that don't work in every 25, we do 38 times 10, which is 380. Now, this is when we're not considering the range, n is 980 to 1,004. If we're considering that range, then there are some cases, there's 2 actually, that don't work. So we have 980 to 984, and 990 to 994. These both grant us 5 each, so we have 10 here that don't work. So we should add the 10 to the 380. So 10 plus 380 gives us the total number of numbers that don't work, or 390. So then we have the number of numbers that don't work. We can do the amount of total numbers, which is 1,000, subtract the number of numbers that don't work, which is 390, to get the number of numbers that work, which is 610. And this is our answer. We're solving problem 9 from the 2025 AMY 2. There are n values of x in their interval 0 is less than x is less than 2 pi, where f of x equals sine of 7 pi times sine 5x equals 0. For t of these n values of x, the graph of y equals f of x is tangent to the x-axis. Find n plus t. For this problem, well, we have these three equations here, right? And we know that for this to be equal to 0, what's inside of this sign has to be equal to something, positive integer k times pi. So therefore, we can say that if this is 0, 7 pi times sine of 5x is equal to k pi. Notice the pi's cancel out there. So we have sine of 5x is equal to k over 7. Now, for the solutions, right? So first, well, we see that in this case, sine of 5x, well, 1 is less than or equal to sine of 5x, and that is less than or equal to 1. And we know that k is between negative 7 and positive 7. Then the number of solutions here, well, we can just start counting, right? So what we want to count is just k's, right? We want to count number of ways, or no, so it says for t of these n values of x, the graph is tangent to the x. So here in this case, we're solving for n. So we have values k is negative 6, negative 5, negative 4, dot, 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 negative 1, 1, 2, to 6. These each have 10 solutions each. And since there's 12 numbers here, 10 times 12 is 120. We have the extremes. K is negative 7, 7. Each of these have 5 solutions each. So 2 times 5 is 10. And k is equal to 0 yields 9 solutions. Altogether, 120 plus 10 plus 9 is 139. Therefore, n equals 139. However, there are some values that do not satisfy this. So in order for in order for it to be tangent to the x-axis, the sign has to be the same. But there are cases where the sign is not the same, the positive and negative sign in front. So it means that when it's not tangent, one thing is above positive and one is negative. And these values have k is negative 6 to positive 6. And then we also have negative 7 and 7. So this is 2 off. So therefore t is 10. There's 2 off of these. So if we have 10 in our t and our n, we can simply sum for our answer, which is 139 plus 10, which is 149, and is our answer for this problem. We're solving problem 10 from the 2025 Amy 2. 16 chairs are arranged in a row. 8 people each select a chair in which to sit so that no person sits next to 2 people. Let n be the number of subsets of 16 chairs that could be selected. Find the remainder when n is divided by 1,000. So let's just let lowercase n be the number of ways, arrangements, like you can pair people up, right? So you want to pair people up. The number of ways to do that, you want to find that. And then you want to find the rest of like the ways you can arrange the rest of the people. So therefore, for this problem, for this specific solution, we want to use the stars and bars technique. So if you have n people and you want pairs, right? There are many ways to select a pair, but if you have n people and select a pair, you have basically n choose 8 minus n ways to do this. Then, with the remaining people, you have 9 minus n people, and then you'd have n plus 1 spots to fill. So, if you have 9 minus n people and n plus 1 spots to fill, then the number of ways to do that using stars and bars would be 9 choose 9 minus n ways. Therefore, the total number of arrangements is these two multiplied. So we want the sum of, if we do multiply these two together, 9 choose 8 minus n times 9 choose 9 minus n. We want to find the sum of these. So how would we do this? We want to find specifically the sum where there are 8 pairs. We want to find the sum where lowest number of pairs is 8, max is 16. So what we can do is we do sigma notation. This is n starting at 4 and ending at 8. So once you compute this, this is going to be equal to 2907, where we do mod 1000, giving us the remainder of 907 as our answer. We're solving problem 11 from the 2025 Amy 2. Let S be the set of vertices of a regular 24-gon. Find the number of ways to draw 12 segments of equal lengths so that each vertex in S is an endpoint of exactly one of the 12 segments. So for this problem, it's going to require pretty complicated insights for the solution at least. So what we can do is we have this length D, we have a length D, right? Such that you have a vertex and it connects to another vertex D units away. Therefore, you basically want to just sum the lengths D. D is 1 to 12, right? Basically. Now what we can do is we can let all the lengths of the 24-gon be just set to 0, 1, all the way to 23 mod 24. Now notice, for any chord of equal length, we're going to have the pair V, comma, V plus D, where D is greater than or equal to 1 and less than or equal to 12. Then we have G, a variable G, where G is, we let G be the GCD of 24 and this length D, right? And for this length G, we're also going to have to incorporate another point M, where M is G disjoint cycles away, and the length is 24 over G. Now, the reason why I had this complex table setting up is because, frankly, I don't want to solve it during the problem because it's going to be really redundant. But once we've basically clarified M is 24 over G, G is GCD of 24 and D is 1 to 12, we can start solving. So, of course, we're going to use your logic. If we have C sub M disjoint cycles, if we have 0 for n of D, 0 solutions. If M is odd, we have 1 if M is equal to 2, and 2 if M is an even number greater than or equal to 4. Thus, we have n sub D, where we basically just want to sum 0 if M is odd, the ones if M is equal to 2. I'll just write 2. And 2 to the power of g for m is even and greater than or equal to 4. Hence, we can start plugging in the values of d. I like to think of this as sort of a process, right? Say you have d is equal to 1. And the 1 goes into the g, and the GCD of 24 and 1 is 1, and then that 1 gets plugged into here, which is 20. And 24 over 1 is 24. So we know that m is an even integer greater than or equal to 4. So you have 2 to the power of 1, which is 2 solutions. So you can keep on doing this redundant process until you have all of them solved, even d is equal to 12, where you then want to basically just sum up all of these numbers. And once you sum up all these numbers, 2, 4, 8, 16, 2, 64, all of that, you will get that the total sum of all these bottom numbers, again, is going to be 113. And 113 is going to be our answer for this problem. We're solving problem 12 from the 2025 Amy 2. Let A1, A2, all the way to A11 be an 11-sided, non-convex, simple polygon with the following properties. For I is greater than or equal to 2 and less than or equal to 10. The area of the triangle A sub I, A1, and A sub I plus 1 is always 1. For every integer I is greater than or equal to 2, less than or equal to 10. Cosine of this angle is equal to 12 over 13, and we know that the perimeter of this 11 gon is always 20. And this sum basically here simplifies to this, and we want to solve this right here. So what we can notice is that this is a form that you might actually be pretty familiar with, because this basically is literally just a Pythagorean theorem. You have the negative b, and then you have the square root, right? Except only it's simplified, and then you have the denominator. So what we want to solve for is probably going to end up looking like this right here, the Pythagorean theorem. So the first thing we want to do in this problem is set variables to certain lengths to see if we can make do with anything. And we can do trial and error on the first triangle. So if we set A1, A2, this length is x, A1, A3 is y, right? And then we have the area of this triangle is equal to 1. Now the area of a triangle can be solved in various different ways. But for the sake of this argument, we want to use it, the specific formula for the trigonometric area. So it's going to be 1/2 xy sine theta is equal to 1. So here, well, we have that theta is less than angle A1, A1, AI plus 1. And then, basically, from here, what we can do, since the cosine of this angle is cosine angle theta, we'll just say theta is this angle, right? Cosine theta is equal to 12 over 13. We know. So that means sine theta is equal to 5 over 13. Therefore, plugging this in here, we can isolate xy, which is going to be equal to 26 over 5. Now, this was just the first triangle, but we can repeat this process for triangle A sub I, A1, AI plus 1. And from this, we find out that our length A sub 1 a sub 2 is equal to a sub 1, a sub 4 is equal to, eventually, the length a sub 1, a sub 10, which is x. Similarly, a sub 1, a sub 3, a sub 1, a 5. This is eventually equal to the length a sub 1 and a sub 11, which is equal to y. Now in this case, to find this sum, we would use a Pythagorean theorem, and we have a third side, right? If there's 9 triangles and there's a third side of the 9th triangle, right? We use the Pythagorean theorem, so you basically just sum the squares. So you have x squared plus y squared minus 2xy cosine theta. From here, we're basically cruising, right? So you have x squared plus y squared minus 2xy is equal, 26 over 5 times cosine theta, which is going to be equal to 12 over 13, yeah. All of this basically simplifies x plus y squared minus 20. And since we have 9 of these sides, right, we know the perimeter is 20, so you square root it, multiply by 9, and add, all right, so, there's 9 of these sides, right? For simplicity's sake, let's just set a to be equal to x plus y. Then we can use this perimeter, right, to get, so here we have 9 root a squared minus 20. You have to add another a to get the full perimeter is equal to 20. And then you basically just have a quadratic, right? You want to isolate a, so you can subtract, divide, square. You get 4a squared plus 2a minus 101 is 0. This is now a simple quadratic where we have a is equal to negative 1 plus or minus 9 root 5 over 4. So we have it in the exact form over here. So that's our answer. We have 1 plus 9 plus 5 plus 4, which is going to be equal to 19, our answer for this problem, and we are finished. We're solving problem 13 from the 2025 AMY 2. Let the sequence of rationals x sub 1, x sub 2, ... be defined such that x sub 1 is 25 over 11 and x sub k plus 1 equals 1/3 times x sub k plus 1 over x sub k minus 1 for all k is greater than or equal to 1. Then x sub 2025 can be expressed as m over n for relatively prime positive integers m and n. Find the remainder when m plus n is divided by 1000. So for this problem, it begins with some algebraic manipulation right here. We see that this is not its like most simplest. We don't like how it looks here because we have a reciprocal, and we don't like that. So what we want to do is first simplify this bit a little more. So what we can do, we do x sub k plus 1 equals 1/3, and we just put x sub k on the denominator. So this is x sub k squared minus x sub k plus 1 over x sub k. Now we realize in this case, this is the top. You see, it looks like a familiar form, right? And it's familiar because this is the form of one of the terms of a cubic polynomial. So if you multiply this by x sub k plus 1, all of that just cancels out to x sub k cubed plus 1. So we can do that. x sub k plus 1 equals, I'm going to put the 3 on the bottom now, but when you multiply this by x sub k plus 1, we're going to get just x sub k cubed plus 1, all divided by 3 x sub k, and then you're going to have to divide by x sub k plus 1, what you multiply to get from here to here. Now, the problem, it says that x sub 2025 can be expressed as a fraction m over n. Therefore, we can let x sub k be m sub k over n sub k, and x sub k plus 1 is therefore m sub k plus 1 over n sub k plus 1. Plugging it into here, m sub k plus 1 over n sub k plus 1 is equal to m sub k cubed plus n sub k cubed over 3 times m sub k, n sub k, and m sub k plus n sub k. Now this here, what we can do in this case, we can we can factor out a term. This one now, and this becomes m sub k squared minus m sub k n sub k. Should put parentheses. And then you do plus n sub k squared over 3 n sub k times n sub k. So here, this is the point where you realize this can be simplified even more when you just want to sum m and n, the numerator and the denominator. So it does not become, but we want to solve for 3 m sub k plus 1 plus n sub k plus 1 is equal to, I should probably write this here. This is equal to m sub k squared plus 2 times m sub k n sub k plus n sub k squared. So we see this is a square, and we can divide by 3 to get that m sub k plus 1 plus n sub k plus 1 is equal to m sub k plus n sub k squared all over 3. Now this is simply what we get. So all we have to do is literally just list out the terms and then do mod 1000. After doing that, you will obtain our answer of 248. So that is our answer for this problem. We're solving problem 14 from the 2025 AMY 2. The problem reads, let triangle ABC be a right triangle with angle A equals 90 degrees and BC is 38. There exist points K and L inside the triangle such AK equals AL equals BK equals CL equals KL equals 14. The area of the quadrilateral BKLC can be expressed as n root 3 for some positive integer n. Find n. The first thing we can do is draw out the triangle ACB. We know that angle A has to be 90 degrees, and we let points L and K, they have to be equal distance. They have to satisfy basically all of these. So basically, now that we've drawn it out, we can see that it might be hard to see if you draw it out because it'd be hard to, but by using these properties, we can see that this triangle KAL, is equilateral, meaning each angle is 60 degrees and each side is of equal length, and two of these triangles, AKB and ALC, are isosceles, meaning that these two angles are equal. So the main insight for this problem is you basically do all this angle chasing, right, to find eventually the desired area. So you want to find a desired angle that will greatly help us solve this problem. So what we can see or observe is that if we have, let's just let angle AKB be 2 times theta. This makes it a lot simpler. If it's 2 times an angle of theta, then that means angle that means angle KBA must be measured in 90 minus theta degrees. We know that, again, I'm just going to write it again, but angle KAL is 60 degrees. So we also know that this one is 90 minus theta. So 90 minus theta plus 60 degrees, you're going to find this angle. So we find that angle LAC is equal to theta minus 60 degrees. So theta obviously has to be greater than 60 for this to be possible. We know that LAC is theta minus 60. So we have this property right here. And what we can notice is that we also have an angle of angle ALC, which is 300 degrees minus 2 theta, the angle right here. Therefore, we have angle KLC being simply 2 theta degrees. Therefore, we know that this angle, if we draw a line from C to K, this angle is 2 theta. So we have these triangles are equal. They are congruent because they have these properties. They have congruent angles. So what we can now do is we can rotate the said triangle around this point, the center of KAL, such that it forms a triangle BCD, where basically BCD is made up of 3 quadrilaterals and the inside of triangle KAL. We know that these quadrilaterals, the 3 smaller quadrilaterals, are equal to the area of BKLC. So what we do is we've basically just formed a larger shape to deal with. So if that's true, we formed a larger shape. We know that the area BKLC, well, we have to see that this is the whole area of the new triangle BCD, and then you subtract the inner triangle KAL. That leaves us with the area of the 3 smaller quadrilaterals that each one is equal to the area of quadrilateral BKLC. Therefore, to find the area of one of the quadrilaterals, we have to divide by 3. If we divide by 3, we can start solving, and this gives us 361 root 3 minus 49 root 3 over 3 using what we are given. Therefore, our answer is going to be 104 root 3. So we are asked to find positive integer n. We see there's a root 3 and there's a 104. Now, I didn't say this earlier, but triangle BCD is also equilateral with a side length of 38. meaning that each side is 38 and each angle measure is 60 degrees. So 104 is our answer for this problem. We're solving problem 15 from the 2015 Amy 2. There are exactly 3 positive real numbers k such that the function, that thing right there, defined over the positive real numbers, achieves its minimum value at exactly 2 positive real numbers x. Find the sum of these 3 values of k. So what we know is that x has a positive integer domain. So we have something to do with minimum values, right? Now, what we can do for this problem is we set a minimum value m. So minimum, just say, is m. We know this minimum occurs at 2 positive real numbers, x. So let's call them x equals alpha and x equals beta. Then this equation right here becomes x minus 18, x minus 72, x minus 98, x minus k minus mx squared equals 0 because there's a square. This is true. But we know that when this is true, this has to be factorable into a square of these 2 roots. So this basically has to be equal to x minus alpha squared, x minus beta squared. Now, basically what we can do now, the reason why we've done this, well, we've kind of overcomplicated it with variables, is so that later we can find a more elegant solution for this. So if we have this, right, what we want to observe is that we want to find the coefficients here to get an equation for k successfully. So you have to know some kind of advanced math, because in order to find the coefficient of this, you have to use Vieta's formula for, I believe it's monic polynomials, x to the power of n minus 1. You basically just sum the roots and then take the negative of it. So the coefficient of this part is negative 18 plus 72 plus 98 plus k. That's the coefficient there. Now you want to find the coefficient here. Well, for this, if we multiply just x minus alpha, x minus beta, that x minus alpha times x minus beta is x squared. What is that? Minus x alpha plus beta. Basically, you want to see that when you multiply these two together, right? You get x squared minus beta x minus alpha x plus alpha beta, which here is x squared minus x alpha plus beta plus alpha times beta. Now, the whole reason why we take the coefficient is because we want the coefficient of the x cubed term. That's basically what we're doing here, and it's might be hard to spot that. But if we multiply one of these out, we get this. We have to multiply this by this again. And the only way to get an x cubed is because you're multiplying here again. It's when the x squared coefficient from the other product right here multiplies into this. And our coefficient is going to be negative 2 times alpha plus beta. So we can cancel the negatives and say that the sum of the x values alpha plus beta is 94 plus k over 2. Now this equation is going to be important for us later, But for now, what we can do is we can start plugging in the roots to the original equation. So we're going to have negative m times 18 squared is going to be just equal to 18 minus alpha squared times 18 minus beta squared. And you can repeat this process for all the roots we have. We have 18, 72, and 98. Once we do that, we find that with the unique properties of m, all the m's just cancel out when you have 72 minus alpha times 72 minus beta over 18 minus alpha times 18 minus beta gives us plus or minus 4 because the m's cancel out. Again, we can repeat this process to get 98 minus alpha times 98 minus beta over 18 minus alpha times 18 minus beta is plus minus 49 over 9 by using these equations. Then we have 4 cases because there's 2 cases here, positive or negative, and positive or negative. So we can just consider the first case, case 1, where we have a 4, positive 4, and a positive 49 over 9. We eventually see that through the equations from here, this case does not work because it yields us a negative value, and we cannot have negative values because the minimum value has to be a positive real number. So we can keep on repeating this trial and error process. We only have 4 ways you can do this. We have plus 4 plus 49, plus 4 minus 49 over 9. We have minus 4 plus 49 over 9, and minus 4 minus 49 over 9. Now, what we can do for this problem is we literally just rinse and repeat for all of these cases, right? So in the end, what we're going to yield with, we want to sum all these that work, right? So, case 1 doesn't work, and we want to try these other cases if they do work, and we want to solve for their case. So, when you solve for their case and sum them, so you want to solve for a case, so case of 1, case of 2, case of 3, if they work, and we see that they do when you plug it in by using that equation. You can basically denounce that the sum of all these is 240, which is our answer for this problem.